Hello and welcome back to another edition of Physics Online, where today we're going to talk about relative motion and independent velocities. Let's start off our discussion with a problem. Relative to an observer on the sidewalk, car B is traveling 60 meters per second and is being followed by car A, which travels at 40 meters per second. In other words, imagine you're standing on the sidewalk over here watching these two vehicles go by. Here's some questions. What is the velocity of car B relative to car A? That is, if you are in car A, what would you say the velocity of car B was? Another similar question, what is the velocity of car A relative to car B? That is, put yourself down car B and look back and ask yourself, what velocity do I see car A moving at? And then another question, suppose car A was moving at 60 meters per second. That is, instead of 40, suppose this car was moving at 60. What is the velocity of car A relative to car B? So push that pause button and we'll come back and compare answers. So here's our answers. What is the velocity of car B relative to car A? Well, if you're in car A, you would say that this vehicle in front of you is moving 20 meters per second. As a matter of fact, it's completely comparable to if you were at rest, car A was at rest, and he saw a vehicle going by at 20 meters per second. What is the velocity of car A relative to car B? Well, looking back, individuals in car B would say, well, it's moving in the opposite direction at a velocity of negative 20 meters per second. And then the other question, suppose car A was moving at 60, suppose this was 60, what would the two observers observe in terms of their relative velocities? Well, they would say they were basically at rest with respect to one another. In other words, the distance between the two would always basically remain constant. And so if that's the situation, then we say that we're at rest. So you can see that motion is indeed relative. That is, whether you're going at zero velocity or 40 meters per second or 20 meters per second, it depends upon your frame of reference. So that's what we mean by motion is relative. As a matter of fact, let's take a look at this question. Is there a place in the universe where we can be considered to be at absolute rest? That is a place where everybody would agree that, okay, the velocity is zero at that particular point in space. And it turns out the answer is no, there is no such place. For example, you might say that while you're sitting at a table and you're at rest on the Earth's surface, but suppose we look from the point of view, a different frame of reference of an observer at the center of the Earth. Okay, now we know the Earth basically is rotating on its axis. Okay, so somebody at the center of the Earth would say, well, everybody and everything on the Earth's surface is moving, and it moves such that basically there's one rotation every 24 hours. Well, then maybe the center of the Earth is a place that we can all agree is absolutely at rest. Well, we know that's not true either, because the Earth, of course, is orbiting around the sun once every 365 days. Well, maybe the sun can be considered at absolute rest relative to everything else, and that also would be incorrect. That is, the sun and the planets, our entire solar system, are orbiting about the center of our galaxy. And the process continues. Even our galaxy is moving relative to other galaxies. So basically, this is what we're talking about when we say motion is relative. In some circumstances, you may consider yourself at rest, but from a different point of view, a different frame of reference, then you could be moving at 20 meters per second, 1,000 meters per second, 1,000,000 meters per second. That's what we mean by motion is relative. Okay, let's move on to another question here. Suppose we talk about a boat in a river, and we're talking about the velocity v sub b is the velocity of the boat relative to the shore. In other words, that's our frame of reference. Okay, and we talk about the velocity of the boat basically in still water. There's perhaps it's a pond, and so the boat provides a certain velocity due to the motor, and that's what v sub b is. On the other hand, v sub c is the velocity of the river current. If if there's a current in the river, then we're on the shore and we could measure that current, how fast the water's moving. And then V sub r is the resultant velocity of the boat relative to the shore. In other words, the boat's velocity may be a little more complex because there may be a river current, a V sub c. Here's an example. Suppose we have a boat that can travel at 3 meters per second relative to the shore. The current in the river is 2 meters per second. What is the resultant velocity of the boat if it travels downstream? That is, if it goes with the current. And we can talk about vector addition. The resultant velocity should be the vector sum. So draw a little vector diagram here. Push that pause button. And let's come back and compare answers. So here's our answer. Obviously, we'd be going faster. Our resultant velocity would be 5 meters per second as measured by someone on the shore. If you're in the boat, you say your boat's moving 3 meters per second, but then the current is taking you downstream at 2 meters per second. So on shore, they would say, no, your velocity is actually 5 meters per second. Let's take a look at this question. What is the resultant velocity of the boat travels upstream, that is against the current? Push the pause button and write down a similar vector diagram and the answer. Here's our answer. First of all, our boat is going against the current, so it's going upstream in the negative direction. Basically, I'm saying the upward direction is negative and the downstream direction is positive. So I have a negative velocity going up. The current is going downstream in the positive direction, 2 meters per second. And so our resultant velocity, as measured by someone on the shore, would be negative 1 meter per second, where the negative sign indicates we're going upstream. In other words, we'd appear to be moving a little bit slower because we have to fight against that current. Now here's a question. Suppose the current was actually moving at 3 meters per second. What would somebody on the shore measure the velocity of our boat if it was moving at 3 meters per second downstream? Well, I hope you can see that the 3 meters per second downstream and then the negative 3 meters per second through the velocity of the boat would basically cause the boat to appear to be at rest relative to the individual on the shore. Let's take a look at another example. Suppose we have a boat that can travel at a velocity of 16 meters per second east in still water, that is with no current at all. But in this case, suppose we have a river that actually has no current and is 136 meters wide. So how long does it take the boat to go directly across the river? Okay. In other words, we have a boat going from one bank to the other bank on the river, and there's no current. So how long will it take? Push that pause button and see what you come up with. Let's see what we have for answers. Here's my riverbank. Here's one riverbank here, and here's the opposite riverbank. Here's my little boat, and it has a velocity 16 meters per second this way, and it's going to go across the river. The river is 136 meters wide, and we know velocity is distance over time. Now, if the river has a current of 9 meters per second south, how long does it take the boat to reach the other side of this river, which is still 136 meters wide? In other words, here's my riverbank, here's one riverbank, and the water is here, and here's the other riverbank. My boat is moving this direction, trying to go across the river at 16 meters per second, but there's a current acting downwards at 9 meters per second. So as you know, our boat here would actually travel this diagonal path and have some resultant velocity. So my question remains, how long will it take this boat to go from this point right in here to this point here? Keeping in mind that there's two independent velocities at work here. There's the horizontal displacement of the boat due to, let's see, what's taking it horizontal? Which velocity component is doing this, and what's the value of that velocity component? So answer these questions and see if we can figure out how much time it takes the boat to go from here to here. Push that pause button now. So there's two independent velocities at work here. One is the velocity of the boat, and the other is the velocity of the current. In other words, one basically is not affected by the other. The horizontal displacement of the boat, that is, it's moving horizontally, is due to the horizontal velocity component, that is, velocity of the boat, 16 meters per second. So if that's true, the velocity of the boat can be expressed as the distance it travels divided by the time, or the time equals that distance, and it has to cover the distance 136 meters horizontal. That's the width of the river, and it's traveling at 16 meters per second. That's the velocity of the boat. And again, we come out with 8.5 seconds, the same as we did up here. Now, it might look kind of strange, but you might say, well, look, the boat's traveling this longer diagonal distance. That's true, but it turns out this resultant velocity will be greater, and so the time will still be the same. Another way of looking at it is this. Imagine this diagonal displacement consists of two independent motions. There's a motion horizontal, which basically is due to the velocity of the boat, and then this downward motion due to the current. And the process continues. There's a horizontal displacement and then a downward displacement due to the current, the horizontal displacement, and then a downward, and so forth. And if we add up all of these horizontal displacements, it would add up to the width of the river, that is 136 meters wide. Okay, that's the width of the river. And it's the boat it's actually its motor going at 16 meters per second, which is taking it horizontally, these horizontal displacements. So that's why we have to use that in our equation, and we end up with the same amount of time to get from here to here as it was to go from here to here. Let's move on to another question related to this river problem. How far downstream is the boat by the time it reaches the other side? In other words, it's traveled not only horizontally, that 136 meters to get to the other side, but it's also traveled vertically. And again, there's two independent velocities at work here. The vertical displacement of the boat is due to, well, what's our choice here? Velocity component, which is, and put in the value of that velocity. And see if you can solve this problem in two different ways. One way is basically to use the equation that we used in the previous problem, velocity is distance over time. Another way is to use a trigonometric function and to think about this angle right in here, this angle called theta. Okay, so push that pause button and see if you can figure out what this vertical displacement is. We'll call it y. The vertical displacement is for this boat. So here's our answer. The vertical displacement of the boat is due to the vertical velocity component, that is the downward component of the current, which is going at 9 meters per second. And we can figure this vertical displacement by that velocity, 9 meters per second of the current, times the time it takes to get across the river, and we come up with around 76.5 or 77 meters. Now the other way to solve this problem is to use the tangent. The tangent of this angle is the opposite over the adjacent, and the opposite side is what we're looking for, that vertical displacement y. The adjacent is the width of the river, which is 136 meters. Solving for y, we get 136 times the tangent of that angle. We need to figure out what that angle is right here. Well, this relates to the problem below, which is calculate v sub r, the resultant velocity of our boat, and we're going to accomplish this by using vector addition. So here's the situation. The boat is going horizontally, or trying to, at 16 meters per second. The current is acting down 9 meters per second. We can find this angle theta and use that right up here. Okay, so figure out what the angle is, figure out what the vertical displacement is, and also find this resultant velocity of our boat. Push that pause button and get out your calculator. So here's our answer. First of all, we can use inverse tangent to find this angle. Inverse tangent is the opposite, which is 9 over the adjacent, which is 16. That gives me around 29.4 degrees. And if you put that answer, that value for the angle right up there, then you should come up with pretty close to 77 meters. So there are indeed at least two different ways to find this vertical displacement of our boat. Now to find the resultant velocity, we can use Pythagorean theorem. Square root of 16 squared plus 9 squared gives me around 18.4 meters per second. at an angle of 29 degrees south of east. Now let's take a look at this next problem. It's related. Using the resultant velocity, that is this right here, and the diagonal distance, calculate the time it takes the boat to reach the other side of the river. And it should come out to be the same 8.5 seconds that we found previously. We're going to find out this diagonal distance, because you know this distance and you know this distance, so use the Pythagorean theorem to find that diagonal distance. And then we're going to use my resultant velocity, this right here, and calculate the time it takes a boat to reach this point to this point. Push that pause button and get out your calculator. Here's our answer. The horizontal distance from one bank to the other is 136 meters. The vertical displacement for our boat was 77 meters. Using the Pythagorean theorem, we come up with this diagonal distance the boat travels to be 156 meters. And it moves at a resultant velocity, which is the ratio of the distance over the time. So the time is solved by the distance, which is 156 meters, and our resultant velocity, which we found up here to be 18.4 meters per second. So again, it comes out to 8.5 seconds. So we see that, yes, if there was no current, we could go directly across the river using the velocity of the boat of 16 meters per second, and it takes 8.5 seconds. But if there's a current, then we have a longer distance to travel, but then again, the resultant velocity is greater, and the ratio comes out to be that same time of 8.5 seconds. Now let's go on to one final question, and then we will leave this river. Question: what heading or direction must our boat take if it is to go directly across the river? In other words, we want the boat to go directly across the river. There's still a current, 16 meters of 9 meters per second. The velocity of the boat is still 6 meters per second. What is the angle? We need an angle to be able to figure out what the direction is to be able to go directly across the river from one bank to another. Push that pause button and let's come back and compare answers. So here's our solution. If we want to go directly across the river, we're talking about going from this point right here to this point right here. Okay? But we know we have to point our boat upstream because the current is going to try to drag the boat downstream. So we need to find this angle right here. That is the direction that our boat has to travel in order to be able to go from here to here. To find that angle, we simply use the inverse sign because it's the opposite, 9 meters per second for the current, over the hypotenuse, which is the velocity of the boat, 16 meters per second, and we get 34 degrees north of east. That would be the heading if we want to be able to go directly across the stream from here to here and to be able to overcome the current. Now here's the question: how much time would it take the boat to go from here to here? Would it be the same as we got in the previous part of the problem, 8.5 seconds? Well, it turns out it actually takes a longer period of time, and as you might expect, it takes a longer period of time because now this velocity of the boat, remember, any vector can be broken up into two perpendicular components. So in other words, there's a component of the velocity of the boat which is indeed taking it across the river, but then there's another component of this velocity which has to be used to overcome the current. So indeed it takes a longer period of time because of overcoming this downstream current to be able to get from this point to this point. So that concludes our discussion of independent vectors, velocity vectors, and relative motion. Thank you for tuning in, and I hope you learned some physics.